So let's continue. Last time, a student, obviously, he knows chemistry. So he pointed out that butadiene should have 4 carbon, and indeed it is. So I revised this particular page and I posted already. So we do have 4 carbon, and then explicitly I also drew the 6 hydrogen around. Then the question is whether the 4 PZ pi electrons will really form something like this, or they would rather delocalize in order to have even a lower energy. So that is the problem about butadiene. So let me continue on with our discussion on molecular levels. So now we understand the full description has to do with 3 terms. Now for the moment, let's consider the situation where we are playing with a gas of molecules and in the microwave or far infrared region. We already know that with such an incident EM wave, it will not be sufficient to excite anything to the vibrational level because the energy does not fit. It's not enough energy for the h bar omega to get up there from the microwave EM wave, all right? So thereby, we already have this idea in mind that will have something to do with transitions between rotational state. That is to say, from one L to another L, okay? But all the things will happen in the same lowest vibrational level. So that will be called the rotational spectrum. That is to say, we are worrying about transitions between these levels, okay? Not even enough to do that, okay? Remember, I have exaggerated, I draw it bigger for you to see, but basically a big series of this is still within this energy. Because remember, a typical spacing here is just 1% of this business, okay? So this is just to let you see. Otherwise, it is much smaller scale hidden here, okay? So for that, we look at the energy of the rotational levels first. The rotational level is this form, L times L plus 1 times this constants, h bar over 2I. So you plug in 0, 1, 2, 3, you will see that now these are the L number, okay? Then you already see that it starts from 0, 1 unit of this h bar over I, okay? Now, if you include a 2 here, that will be 2 units, okay? Very often you don't write I, but 2I, then that will be a 2. That will be a 6, and so on, okay? So, nonetheless, it's the same result. So, you have 1 unit of this, 3 units of this, 6 units of this, 10 units of this, okay? Now, this is this alignment, blowed up here, okay? Now, second point, transitions. Transitions has to do with going from here to there. You absorb a microwave pointer, EM wave, right? We have done this light matter interaction previously. The same thing. So it has to do with the difference. Therefore, we want to see the difference as well. So what is this difference? Okay, now you see that this is more. This is 2 times that. Now, 3 unit, 1 unit. The difference here is 2 unit, right? So you have this 2 times, okay? And then you have 3 times, then you have 4 times. So this spacing is getting bigger and bigger in steps. That's the point, okay? Now, 2 things here. One is about this energy, how they aligned. So it's like that. Second is about the difference, okay? Now, obviously, here we stress something like delta L equals plus minus 1. Okay, so that's why we only work with this neighboring separation. When you see this, I think something should come into your mind, has to do with selection rules, right? So we will discuss that. So this picture brings out what we just discussed. The difference is 1 unit. So you start from 0 here, 1 unit, okay? Then you have 2 units. So 2 units goes from here to there, all right? 3 units goes from there to there, okay? So what does it mean experimentally? It means the following. There will be rotational spectrum of a molecule that happens in microwave range. So this E photon corresponds to 0.001 eV order. Okay, you shine in such energy, microwave range, and you will see some regular absorption. Okay, now this is the transmission. If you don't have anything, it will be perfectly transmitted. If your jar, the sample, has nothing, come in, go out, total transmission. But if you have some gas of molecules in it, and in this particular energies, you see a dip, meaning less microwave will go through. They are absorbed by the molecules. So when you see this value, it means some molecules here absorb the microwave, go up to here, okay? L equals 0 to L equals 1. When you see a dip here, it means some molecules already here. Now, room temperature can do it, all right? Now absorb this particular microwave energy and go up to there, L equals 2, okay? And so on. Okay, do you understand? Do you understand? Okay, several things. The range is important. Then the pattern is important. You see some kind of regular, equally spaced dips. When you do absorption experiment, it will be peaks going up, okay? At that frequency, absorbs, okay? But still equally spaced, rather regular spikes. So here is an example, CO, rotational spectrum. Here given in Hertz. You look it up, okay? So this is in the far infrared and touching microwave. You see the regular pattern, equally spaced, okay? Note that this is absorbance. So this is absorbing. The one that I show you is transmission. So transmission, you see dips. You interpret the data as absorbing. You see these peaks, okay? Now, this page is an appendix or an aside. I try to bring out one piece of physics. Where does the selection rule comes from, okay? We have been talking about L equals 1 to L equals 2, and so on, all right? Now, obviously, if you first excite it and then turn off the beam, this will come back to here. Well, you know time-dependent perturbation theory, right? Stimulated absorption equals the emission. Well, at least related to the emission rate, right? So even in the emission spectrum, you will also see such pattern. And now I would like to discuss why do we have these selection rules. Physics is simple. We don't need many different new physics. Why is the dip one not, why the dips, that's a question. Why the dips one is not absorption spectrum? Okay, because the y-axis is transmission. Of course, the interpretation is some microwave is absorbed. You see? Okay? The y-axis of the curve, okay? It starts from 100%. Okay? So now I want to give you the discussion on the selection rules. No new physics. All you need to do is to apply what we learned. So we have EM field, microwave. Well, it's EM field anyway. It should couple to some charge thing. So it is the electric dipole moment. So at this point, the electrons do not play the role because the electron already played the role of forming the bond. Okay? It's more about the positive and negative charge of the two atoms. After the electron's wave function is known, if they are different A, B molecule, okay, not homonuclei, but hetero, different, A different from B, the electrons will tend to shift to one side more, right? Because there's no symmetry when you do LCAO, okay? So thereby, one atom will be slightly positive, one atom will be slightly negative. Therefore, you will have a electric dipole moment. The electric dipole moment has a magnitude equals to Q times the separation, and I simply take the equilibrium separation for this discussion. So this is the magnitude, and then the direction is pointing from the -1 to the +1. Okay, so pay attention to this particular point. We assume the molecule in question has a permanent dipole moment. Okay, we need them to be different atoms to start with so that the electron will distribute unevenly, and then we will have this electric dipole moment. Okay, now you apply a field, there's a dot product, thereby you will pick up, well, depending on where your field points to, you will pick up that projection. Let's say the field is in Z direction. It could be in X and Y, whatever you call it. If it is called Z, you will pick up mu projected on the Z direction. Okay? We are talking about the nuclear motion here, okay? Not the electron. So therefore, the Z component will be the magnitude times the angle. Okay, cosine theta. What I mean by that is actually something like this. I have A sitting here. I have a B. So I'm talking about the two nuclei, and then I have X, Y, Z, and then this is the big theta. Okay, you project it down. This is the spherical coordinate big phi. Okay, so the point is, I will pick up an angle here so that when this goes with that and do the d theta integral, that will not be zero. Okay, and therefore it depends on, I should say, it depends on whether what is L prime and L, because there is some theta dependence here, and then together with this cosine and sine, you do this, then you know that only when L prime and L, they are different by plus minus 1, this integral is not zero. Then you have the transition. That's the point. Okay. Now, for those who are more mathematically inclined, another way to think about it is as follows. Whatever this direction of the field, actually here, it is a direction. Z here, or X here, or Y here. Okay? Now, whatever you pick up, at least for this particular example, cosine theta is Y10 theta phi. Okay? Do you know that? No. Now, if you have forgotten what is YLM theta phi in the form, don't worry, there are tables for you to look up. What I'm saying is that cosine theta is Y1. It corresponds to something like L equals 1. Then you can look up what is the condition when you multiply 3 spherical harmonics, 1, 2, and the Y1 in between. When will that integral be non-zero? What you have in the middle only provide a 1. And the requirement is that these two L prime and L should be at most different by 1. Okay, and that is how the selection rule really comes from. The same argument works even if you have not Z in the middle, but the X and Y component in the middle. Okay, I think you might have used this in earlier atomic physics selection rule discussion. So this is the selection rules. Then you may wonder, what is the application of this? Okay, the application is obvious. Remember, this difference is h bar squared over I. Thereby, I know this is 1 unit. This difference is also 1 unit. So you see this regular pattern, although this happens is twice, 3 times, 4 times. But from the spectrum point of view, you read this thing out, or you read this thing out, but they are supposed to be equally spaced. You read this thing out, you already know this thing. Thereby, by reading this difference out, you get the moment of inertia. From the moment of inertia, if you know what is the molecule, you know the reduced mass, thereby you can calculate the bond length. Pretty easy, right? Now that is experimentally how one can extract the bond length out from reading a rotational spectrum. How easy is that? You see? But there's much quantum mechanics behind it. Okay? So that is the application that I mentioned here. Before we really work on the application, here are 2 pages that is about notation. No new physics, okay? So the point is no new physics here. It's only about notations. Why do we need to care about notations? Because they are data books. Maybe later on you are doing AMO. Now it's very hot branch of physics, atomic, atoms, molecules, and optics, right? So maybe you really need to use some of this thing. So when you look at data book, you see, oh, very different from what we are discussing here, then I hope that you would not blame me at that time. So I introduce some notation for you. No new physics, because we start from here, okay? And then we don't like H bar, we write it as H, fine, nothing. And then the next line, define what the spectroscopists, 光谱學家, 光譜學家, what do they use? They will introduce a rotational constant called the B. That is a property of a molecule, all right? So it is at this place, they write this particular form. Now this is an energy, so they want to use H times a frequency. So thereby this B has the unit of a frequency, nu, hertz, for example, okay? So that's easy. You just take out one factor of H bar, the remaining thing is the B. So this is the definition of the B. So there's nothing new. Again, it is related to the moment of inertia, but a different constant in front, okay? All in all, this is the property of the molecule. The reduced mass, we need to know what are the atoms and then the bond length, okay? In this form of the rotation constant, you will find numbers in hertz. This is the data book version, okay? Now, pay attention. If we use this form, then we can work out L equals 0 is 0, L equals 1 is 2 times, okay? So when you make a transition to L equals 0 to L equals 1, the energy is 0 to 2BH, right? Therefore, in terms of frequency, the rotational spectrum becomes 2B, 4B, 6B, 8B. All right? So you read this thing out, it is 2B. And then from that point on, you can calculate what is the moment of inertia, thereby you will get the bond length. Same thing, but just a rotational constant that many people used. Now, the next page is even worse. Even for rotational constant, there are 2 definitions. So this is one. The other one is very often, you even see rotational constant given in the wave number, centimeter inverse. Just to remind you, centimeter inverse means the following. 1 centimeter, how many wavelengths are there? Okay, so 1 centimeter, the wavelength, there are 60 times in 1 centimeter. Okay, so of course it is talking about the same thing as mu, but in different units. So what is this new B? Has to do with the OB. Okay, I called it B bar, but the chemist will not call it B bar, it's just the same B. So you have to look up, this B is in hertz, that B is in centimeter inverse, okay? Professional business. So, but it is easy for us. We know that in order to change from hertz to wave number, it is just dividing the number by speed of light c. Thereby, we copy through, we only need a factor of c in the bottom. Therefore, this is B bar, okay? Again, the spectrum will give us 2B bar, 4B bar in spacing of 2B bar, okay? And then, if you look up datable, you will see these numbers, okay? I copy a few out. So this is the end of the part on rotational spectrum. So let me summarize. For this rotational spectrum, all occurs in microwave. And then we are playing with one series only because molecules cannot occupy n equals 1, n equals 2, n equals 3, usually in room temperature. But molecules will be spread out here. And therefore, we do see this series of rotational lines. And we are only playing with this series, and there is a selection rule. The selection rule has to do with delta L equals plus minus 1, but under one important condition. The condition is we need to have a permanent dipole moment to start with, because even if this is non-zero, if the molecule doesn't carry a permanent dipole moment, electric dipole moment, the whole thing will be zero anyway, okay? That is to say, we better have slightly shift in charge of the electron in forming the bond so that we do have permanent electric dipole moment, okay? And then we will see regularly spaced rotational spectrum from which we can read out the spacing and obtain the bond length, okay? Now, so far, we cannot extract the bond strength. That is to say, the spring constant, because we have not dealt with vibrational transition. That is what we will do now. So the next part has to do with transition between vibrational levels. Okay? So the first picture is, recall, we have ground state vibrational oscillator, first excited, second excited. They are different by h bar omega, and typically it is in the infrared. Okay? We played with microwaves, thereby we only play with the rotational state here. We cannot excite transitions like that. And now we are going to do that. We need to consider infrared region. So most common, you will excite n equals 0 to n equal 1 oscillator state, meaning the molecule may be excited from here to there, all right? But also remember, in this picture, I only stress the vibrational level, but in fact, a full description should be n equals 0, L equals 1. We will make a transition to n equals 0, L equals 2, and that will be the real problem. Okay? So at the end, you will see, for good resolution, we will be doing something called vibrational rotational spectrum. that has to do with n equals 0, L goes into n equals 1, another L. Okay? You see, both vibrational transition and rotational transition, but go to a different family, a different series are involved. Okay, so that is the point. By considering this vibrational level transitions, we will be able to extract the spring constant. That will reflect how strong the bond really is. So let me start. So the point is, we want to get the spring constant, okay? Now I give you some data first, so that at the end, you see the ballpark range. When we extract numbers out, it is okay. So here I give you some diatomic molecules, the n equals 0 to n equals 1 frequencies. So this is the h bar omega. And then these are the force constant, the spring constant. Okay, now this can be obtained experimentally, thereby you could look for the spring constant. Okay, you measure this, you can got that. Okay, from data we can also extract this first and then obtain that. All right, so look at the ballpark range. It is 10 to the 13 hertz infrared. We can see starting from 10 to the 14 to somewhere to 10 to the 15 hertz. Okay, so this is infrared. In EV, it is this range. So what is the mechanism? Okay, now again, it should be electric dipole mechanism. All right, now think about the two different cases. If they are of the same atom, for example, oxygen, nitrogen, right? So you have O2 and O2. Because they are the same, the electron will distribute themselves symmetrically about the midpoint, okay? And then they are not charged, they are not even slightly positive negative charge, there will be no permanent electric dipole, okay? But if we have different A, B molecules, for example, carbon monoxide, okay, then we will have permanent dipole and more, slightly more, okay? Now, here is a punchline for vibrational business. The vibration will be about this minimum, thereby this distance between the A and B's slightly charged oppositely, okay? The two ions will be, the separation will be changing. So I plot out an R1 here and an R2 here, okay? So sometimes it's bigger, sometimes it's smaller as it vibrates, like this, okay? Get me? Now, that means the following. Now, very important thing, keep this in mind. In this situation, we will have the electric dipole moment changing as the atoms vibrate. Okay? Now, keep this in mind. We need this in order to see vibrational transition when you incident and infrared radiation. Okay, so let's see how it goes. This has to do with the selection rule. So here again, if you care about details, this is the reason. For transitions between vibrational levels, we are dealing with the oscillator state. So this is oscillating ground state, the Gaussian. This is oscillating first excited state. it's a Gaussian multiplied by x, right? That is something like that, okay? The x is called the Hermite polynomial. Nonetheless, we know this, okay? So we have an oscillator n state and an n prime state. We are trying to do the matrix element selection rule to see whether this is 0 or not. There will be a theta phi part, but we already do that. This has to do with the rotational thing, okay? But we are now focusing on the radial vibrational transition. That is the oscillator part. So the matrix element in perturbation theory must have this form: initial, final, the reason that it will make a transition. That is the H prime before, okay? You see, no new physics. Now, let's consider if we only have a constant magnetic dipole moment, not changing as the molecule vibrating, okay, just stick there, still, okay? Now, if it is a constant, the field is also a constant, this whole thing can be taken out of the integral. And now you have this integration between two different oscillator states. But they are orthogonal, okay? So if you only have constant dipole moment, it is not going to work. It will not allow vibrational transition. However, if this mu, as the thing vibrates, now this will be different as the molecules, the atoms vibrate. If it has a non-zero Taylor expansion, now this will be the constant right at equilibrium separation. If you do this first order Taylor expansion, you will pick up d mu dr. That has to do with vibrate. There will be a change in the electric dipole moment, and that will pick up a separation from the equilibrium position, okay? R minus R0 is this thing. I'm vibrating, so R minus R0 is the separation from R0, okay? So it is this part, but I need a constant in front, d mu dr. That signifies whether the electric dipole moment change as the molecule vibrates or not. Okay? Now, if we have this being non-zero, now we argue that this part is not going to matter. It will not give us non-zero integral. So we ignore this term. Then the problem is this term. Okay? So I draw this out, write this out there, and then I have R minus R0. So I have there. Okay? Now this is, after you shift the coordinate, this is harmonic oscillator state n prime with an x in between. This is exactly this integral. And in your homework problem, in sample questions, we have done this before. We know this is non-zero if n and n prime differ by 1. And this is why we have the selection rule, okay? For those who are very mathematically oriented, x is related to a dagger and a. Now, of course, with some coefficient in front, okay? But you see, one term is a dagger, so the two sides must be different by +1. One has to do with a, the two sides must be different by -1. And that is how this thing comes up, okay? Now, if you don't know this, don't worry. The take-home message is vibrational level selection rule is delta n equals ±1. That's it, okay? You don't need fancy physics to understand a lot more other things. I already discussed this, okay? All in all, you need, during vibration, the electric dipole moment is changing. Why am I emphasizing this, okay? I would like to introduce two pieces of important information to you. Your generation should care about climate change, and two molecules are particularly important in this discussion. One, nowadays becomes the bad guy, but it's innocent. Well, it's just happened to be like that. So carbon dioxide. Of course, we have been discussing diatomic molecule, but we can extend what we discussed to bigger molecules. Here we have 3 atoms forming a linear molecules. Now this is an experimental fact. It forms a linear molecules, okay? Now, we have 3 atoms. Each atoms can move in X, Y, Z. So we have 9 so-called degrees of freedom. Okay, I'm doing classical mechanics counting. All right. Now I have a linear molecule, meaning I have a rock. Okay, even I have 3 atoms, it is linear. Okay, meaning I need 2 angles to specify its orientation. So I have a rod, I only need a theta and a phi, that's it, okay? So that means I have 2 rotational degrees of freedom. That will be the theta phi thing, all right? Therefore, I have 9 minus 2 degrees of freedom left. Then I have 3 of them being translational. That means the whole carbon dioxide don't do anything, not vibrating, not rotating, just translating. So it could be translating in Y, your direction, in Z, or in X, okay? So that is the translational degrees of freedom. For those who are taking statistical mechanics ideal gas, this is the ideal gas. The gas is moving freely as a point particle. That is the center of mass translational motion. Okay, you have encountered that many times. Maybe you don't realize it. Okay, now let's do the counting. Total 9 minus 2 for the rotation, minus 3 for the translation. Okay, therefore I will have 4 left. That 4 corresponds to 4 ways of vibrational normal modes. Okay? Again, if you don't follow this, don't worry, you need some classical mechanics and then to back you up. Nonetheless, the fact is that there are 4 vibrational modes, normal modes. Here are the 4, okay? Look at the other 2 first. So this is the symmetric stretching. So something like that, okay? Now, do you see that? As this even, they are not the same molecule. The electric dipole moment is not changing. This longer, that longer, okay? They cancel out, okay? And then there is a asymmetric stretching. Along this thing, maybe something like that. Okay, so here you have this 2 modes. The remaining 2 are the most crucial ones. They are degenerate, okay? They are the symmetric banding, okay? So one is, I think, this is going down, the other is going up, okay? So something like that, or going in front, backward, okay? Now, this is 3 Bose 2 spring classical mechanics problem. If I give you the mass and the K1 and the K, you should be able to derive formula for this normal mode frequencies, okay? Now let me tell you the experimental number. For this is the most concerning one, symmetric banding. There are two modes, 1, 2, 3, 4, okay, good. We count the right number. So this, in terms of wave number, the normal mode happens at 667 centimeter inverse. In terms of wavelength, 15 micron. And then there are other ones also changing electric dipole moment. So this is also in so-called infrared active. Okay, there are transitions between vibrational state that happens in 2,300 wave numbers. Okay, centimeter inverse, 4 microns. All right, so this is the CO2 spectrum in the infrared. Okay, now the resolution is not high. Therefore, we don't care about the rotational transition associated with this. We don't care about that. It's a rough infrared spectrum, not high resolution one, okay? Now, then you see, really, this is transmission, therefore, you see this dip, okay? One at this wave number, 2,300, one is 667, okay? In micron, I give you the number already, 15. So this one, around here, okay? Water, okay, similar thing, but water is not linear. For the rotational thing, when you have three things that is not linear, you need so-called three Euler's angles to specify the orientation. Therefore, there will be one more degree of freedom in the rotational thing. You take out one from the vibration. That's classical mechanics again. And now, look at all this normal mode for vibration. You have this symmetric banding, but now in different, not on a line, all right? Now, do you see that this is slightly negative, this is slightly positive. So when this is vibrating, the electric dipole moment is changing, okay? In fact, all of them have the electric dipole moment changing as the water molecule vibrates. I again give you some numbers, 1600 wave number, okay? And then two nearby in 3,700 wave numbers. So this is the water spectrum in the infrared, okay? So you see big dip here and then big absorption. That means big absorption here in 3,000, more than 3,000. This is 3,600 or so, and then you have that, okay? And here, actually, you also have another dip, but that has to do with the rotational spectrum. So the point is, water has something here, has something there, okay? Now give me a few more minutes. I tell you the problem about greenhouse gas. The sun gives us energy. The sun's surface temperature is about 6,000 K. Black body radiation spectrum, we can plot it out. Then we look for the peak. That is the most intense energy coming in from the sun. It is in the visible, okay? You see, our eyes so well adapt, it evolved into adapting to this sun spectrum. So that's why we are sensitive in this region we call visible. Okay, nice. But when this, now this is higher frequency, okay? That means shorter wavelength. So when this shorter wavelength comes in, the earth absorbs it, we have buildings, we have forests absorb it, and then at the end, we get into the equilibrium about 20 degrees Celsius. And then we also have black body radiation outward. We want to radiate out again, okay? So as not to keep on increasing in temperature. So let's look at the black body radiation curve for 294K. This is our so-called standard average temperature on Earth. So it has a smaller area under the curve because the area goes like T to the fourth, step von Boltzmann law. Okay, I hope that you know it. Well, you will learn it in your statistical mechanics. Then lower temperature means the total energy is smaller, but another point is that the peak shift to infrared. That's why we say this is warm, okay, basically. Okay, so that is to say, this comes in, we radiate this out, and that's the problem. This temperature has the black body radiation. We are trying to get rid of energy, and most energy falls into this infrared. That could be good and bad, because the atmosphere has CO2, has water vapor. Here I show you a measured spectrum from the outside. So this is outside the atmosphere, okay? If it were, the whole thing is uniformly 294 degrees, we expect the spectrum like the solid line. This is the black body radiation for this, okay? But we measure outside, we found there are dips. So here is some missing radiation outward. All right? Let's look at the number here. This is about 667 wave number, okay? And that is due to the carbon dioxide bending, symmetric bending mode. All right, and it is because of this is rather deep and apparent shortage of radiation out there. We say, carbon dioxide absorbed what we want to get rid of, and then it will re-radiate, all right. Only part will go out, but part will be re-radiated inward. So that will keep us warmer than what we want. Now think about it. It is not the bad guy. CO2 is there to keep us warm. Otherwise, we may not be able to survive, okay? But too much CO2 may be a problem because of, this missing part when we want to radiate out there, okay? Now, there are other things. You see some water thing, okay? Water vapor. There is also a big missing part here that has to do with water vapor at 1600 wave number. That is also a bending, this is bending mode of the water vapor molecule, okay? Actually, you also see something here due to water vapor, but that has to do with the rotational end of water vapor spectrum. So this is the so-called greenhouse effect. But now, I hope that you don't just memorize things. There's a lot of quantum mechanics in it. You need to know Schrödinger equation. You need to know vibrational harmonic oscillator physics, vibrational state, how the electron form bonds, how the classical mechanics, what are the normal modes, you hit at that frequency, and then time-dependent perturbation theory of absorption and emission. You see, a lot of science behind this, okay? So I think it is worth your generation to know, okay? So here is just some data about how much carbon dioxide is in the atmosphere over 170 years, okay? Data says it is increasing, all right? So is it due to human activity or some other things, volcano, whatever, okay? Then your generation will, study that or even try to reduce carbon dioxide emission into air. There are many ways out, and there are some very hot research topic along this line. Very obviously, people will try to convince people to cut down emission of CO2. Factories not burning fossil fuels, a lot of things, okay? Reduce emission, reduce production, have contracts for emission. So you need to buy a right, a certificate, so that your factory can emit that much, okay? But even so, there is a technical problem. How are you going to measure emission? Can you be very accurate in measuring this factory emit this much of carbon dioxide? I think nowadays they just use the electricity bill. You use that much energy, therefore you must have produced that much product, and so you have to pay that, okay? There are other ways, actively research to reduce this CO2 in the atmosphere. For example, our economy still rely much on CO2 emission because of many processes in industry will emit that. How about this? We capture the CO2 so produced, okay, and then find some way to store it. Now, there are already things like that, store it underground so that emission will not go into the atmosphere, thereby this problem is at least slowing down, okay? So there are a lot of things that are going on and your generation should know. That's why I spend some time to connect this to our applied quantum mechanics. Indeed, a lot of quantum mechanics is underlying this discussion, okay? So I will stop here today. The next part really has to do with vibration and rotation level transitions. That is the vibrational rotational spectrum that I show you at the beginning. I just flash you a page and then I will stop, okay? I will flash you what we are going to discuss next time. I will explain why do we see such a spectrum in the infrared when we have high resolution apparatus, okay? So from this, we can extract bond length as well as the spring constant bond strength. We will do it on Thursday, okay? So long for now.